Assalamualaikum warahmatullahi ta'ala wabarakatuh, and hello to all. Okay, we're going to start with a new chapter. Chapter 8 is on state non-isothermal reactor design. So this is a new chapter. As I told you earlier, before this we've been learning about isothermal design when there is no change in temperature. But then now we're going to visit a chapter where temperature influence a lot of condition in terms of the reactor design. Okay, let me skip. So what is this chapter all about? First of all, we have to know that there will be altogether 4 chapters that will be covered, which is on the rationale why we use energy balance. And the second lecture is on adiabatic energy balance. And the third lecture we cover on the steady state tubular reactor with heat exchange. And the fourth lecture is on equilibrium conversion. I will basically not cover the lecture 5 steady state CSTR with heat exchange. Normally for an isothermal reactor, the profile will look simply like this. This is the temperature, and this is the volume, and you will get just a straight line. Because you know that temperature is influencing your K. So changing the K will change the volume of the reactor. However, for an adiabatic exothermic reaction, the temperature profile might look something like this. For example, at certain temperature, the volume will just look like this. And similarly with the rate constant, and similarly with the conversion. So this is conversion. We suggest that as the volume increase, there is a possibility that the conversion would not increase to what you are expected. It will achieve equilibrium. Similarly here, it will achieve equilibrium. So there is a concern that if let's say we are using an adiabatic reactor, okay, these are the profile that what you will get. Why energy balance? So what do we have so far? For example, like if it's for a plug flow reactor, we have this design equation for PFR, and we have this rate law for a first order reaction. And when you rearrange everything, you will get something like this, which basically the rate constant is defined as K equals to K1 exponential E over R in the bracket 1 over T1 minus 1 over T2. If we combine all of this information together, this one with what you have this one, basically you will get this particular equation, dx over dv equals to K1, etc., etc. So for non-isothermal operation, K always depends on the temperature. Okay, and temperature varies with reactor length, as we can see earlier from this. This is volume, this is temperature, so it will go something like this. The profile will look like that. So we need either, in order for us to find the information for us to solve, for example, to get the volume of the adiabatic reactor, we need X to be function of the temperature, which is the conversion, or the temperature to be function of the volume. Okay. There are lots of equations that we'll be using. I will go back to this part later when I will not look into it yet. But basically, okay, if let's say we are observing this particular equation, equation 1b, okay, this part, right? I'm trying to express this equation in terms of a graph. What does it look if let's say we have a graph? So what we are plotting right now is basically Fa0 over negative Ra versus the conversion. In an adiabatic reactor, you will have what will look like. It will look like this. The Fa0 over negative Ra, if you remember, it is just a derivation of dV over dx, okay, of a plug flow reactor. And then you remember that for a plug flow reactor, the area under the curve represent the volume of the reactor. So in order for you to determine the volume of the reactor, so we use this particular equation, T over T naught plus delta HRX times X divided by CPA. CP is basically the mean heat capacities, average mean heat capacities. HRX is the heat of reaction. So in order for us to plot this particular graph, okay, there are steps that we can do, which is first we choose what would be our x. For example, like from 0 to 1, okay, so we start with x equals to 0, put it here, then we'll get this is equals to 0, this will equals to 0, and then you got your T naught, T equals to T naught. So basically at this particular point, okay, it represents T equals to T naught. And then when you got your T, okay, when you got your T, what you have to do is basically to calculate your K, because you know, remember that K is equals to K naught, okay, E to the power of E over R 1 over T2 minus 1 over T1, okay, or the other way around. Alright, so when you got your T, you substitute into that and you'll get your new K. And from this new K, you can calculate your equilibrium conversion. Okay, the KC, capital K. And then from here, you can calculate your negative Ra, which is the rate of reaction. And you divide it by the given initial mole flow rate. Okay, so, and then you can get some point around here. Okay, and then so basically this particular point is represented by the Fa0 over negative Ra that you calculate. Okay, and then what you can do is you can switch x from 0, and then maybe you can add, okay, at 0.2, and then you can recalculate using this particular equation. You'll get your new T, go back to this particular equation, K over something, and then once you get your K, you need to calculate your equilibrium constant. Okay, once you got equilibrium constant, calculate back your negative Ra, and then do the same process over and over until you got a full complete, until the conversion extent that you want. For example, like here, you just want to make sure that what would be the adiabatic reactor size for conversion up to 0.9. So you get some plot here, and then you calculate the area under the curve, then you will get your volume reactor volume. Sorry. So if you revisit with this particular graph, so you can see that you can use this particular equation as well as you can use this particular equation in order for you to calculate do the exercise. Let's go to this part. The general energy balance for an open system. Okay, we'll have to revisit our principal and chemical engineering PCE subject, mass and energy balance, this part on energy balance. Okay, whatever that comes in, okay, whatever that comes in is basically the molar flow and the heat coming in, and then the energy that you supply, Q in, and then the work being done by the system, okay, and this is defined as the flow rate out and the heat out, okay. So you look at, in terms of the energy balance, it is given as dE over dt equals to Q equals to this Q minus the heat in minus the work being done plus with the heat F times E in minus F out E out. But for a closed system, this term is become 0. Okay. For an end species, the equation becomes as follow, where basically Q is the rate of flow heat to the system from the surrounding. This is Q. Okay. W is the rate of flow of work done by the systems on the surroundings. And Fi times Ei in is the rate of energy added to the system by mass flow into the system. And Fi Ei out is the rate of energy leaving the system by mass flow out of the system. So this is the rate of accumulation of energy within the system. The resulting equation, okay, based on energy balance for steady state flow system, will become like Q minus the work done, okay, minus FA naught times with theta CPI T minus TI naught minus FA naught XA delta head of reaction equals to 0. How do you get this? I will give you a self-learning note where basically you will need to read from the textbook. It will give you a guidance on how you can prove this. Okay? But you can see here, we get this particular term by introducing the heat of reaction. The heat of reaction is defined based on the following equation. Okay. So basically, this will give you the heat of reaction at the reference temperature. Okay. Normally, this is at 25 degree, for example. But it depends. Sometimes the value can change. For example, it gives you what the reference temperature. Reference temperature can change. And this particular equation, okay, with respect to the stoichiometric of each reactant involved, it can give you the mean heat capacity with respect to the reference temperature. Once you calculate this, then basically it will bring you up to this particular equation. You can start using this particular equation. As an exercise for you, you are required to calculate the heat of reaction for the synthesis of ammonia from hydrogen and nitrogen at 150 degrees Celsius in chemical mode of nitrogen reactor and also in hydrogen reactor. The reaction is given below. So you can see here, this is your TR, reference temperature. Okay, this is head capacity is also given at 25 degree. This is your reference temperature. So if you we'll stop for a while. So this is for lecture 2. I will continue later on. Thank you.